Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture basically we have talked about the seepage in soil, and there we have seen that how you can construct the flow net and what are the different types of lines which will be conforming the flow net, like the equipotential lines and the flow lines. And then we have talked about the flow channels through which the flow will be occurring. And there we have seen, or we have discussed if you consider the square element, flow element, then what will be the discharge. If you consider the rectangular flow element, then what will be the discharge. So, these things we have covered in the last lecture. I hope that you can still recall those things. So, from that point onward we will move forward. So, basically today we will be talking about if you want to construct the flow nets in anisotropic soil. So, for anisotropic soil your Kx is not equal to Kz, right. So, I mean what we discussed in the previous lectures, that all the times we considered Kx equal to Kz, and we have got the Laplace continuity equation which was nothing but del 2h by del x2 plus del 2h del z2 equal to 0. So, that was the continuity equation for the isotropic soil, isotropic with respect to the flow, okay, or the permeability. So, if the Kx is not equal to Kz, then the soil will be considered as the anisotropic soil, and in that situation how you will construct the flow net, because in this case the equation represents two families of curves that do not meet at 90 degree, right. That is the major and important thing, that basically you have the families of characteristics like families of say two curves like flow lines and the equipotential lines. Now, in the earlier case we have seen when we have discussed about the flow nets construction and other things, at that time we have seen that the flow lines I mean all the flow lines intersect the equipotential lines at 90 degree, right. But in this, because the equation of the Laplace equation, that continuity equation will be telling that thing, that you will be getting two families of curves which will be intersecting each other at 90 degree. But if you consider anisotropic soil where the continuity equation is given by Kx del 2h del x2 plus Kz del 2h del z2 equal to 0, at the end if your Kx is not equal to Kz, then this equation, okay, will not tell the two families, I will tell about two families of curves which will be intersecting each other at 90 degree, okay. That quite obvious from the mathematics point of view. So, what we can do in that situation? So, basically we can modify this equation, say equation 2.21 in this way, say del 2h by Kz by Kx del x square plus del 2h del z2 equal to 0. Now, substituting x prime some different coordinate system, say x prime is equal to say root over Kz by Kx into x, we can write that equation 2.22 will be taking the form of del 2h del x prime 2 plus del 2h del z2 equal to 0. So, now basically we are transforming the x axis in such a way that it will take x prime which will be equal to root over Kz by Kx into x, okay, and z will be remaining as it is. So, there is no issue with the z axis. So, now if you look at equation 2.23, so this equation will be telling there are two families of curves which will be intersecting each other at 90 degree, okay. So, I mean in x prime z coordinate system, okay. So, we are transforming the coordinate system, we are transforming the axis, and then we are getting our desired equation, okay. So, now equation 2.23 is similar to equation 2.5. If you see, if you recall, or if you go back to the equation 2.5 which was giving me del 2h del x2 plus del 2h del z2 equal to 0. So, equation 2.23 is nothing but same equation as given in equation 2.5 with x replaced by x prime. That is the only difference we are making, which is the new transformed coordinate, okay. So, as I told you, to construct the flow net now, Adapt a vertical scale, that is z axis, for drawing the cross section. Okay. So, that you do. So, now you can construct the flow net in anisotropic soil in by following these steps. Then second step is adopt a horizontal scale, that is x axis, such that the horizontal scale is equal to root over kz by kx times the vertical scale. Okay. So, now basically you are going to transform, otherwise you will not be getting the families of curves which are intersecting each other at 90 degree. Okay. So, if you do this transformation, then you will be getting that 90 degree intersection. Okay. Now, with scales adapted as in steps 1 and 2, plot the vertical section through the permeable layer parallel to the direction of flow. So, now the procedure will be remaining same whatever we followed for our previous case, like when the soil was isotropic. And then draw the flow net for the permeable layer on the section obtained from step 3 with flow line intersecting equipotential lines at right angles and the elements as approximate square. So, then the matter will be remaining same, right. So, basically now you are constructing flow nets with the help of flow lines and equipotential lines. Now, they will be meeting each other at 90 degree, and the elements you just consider whatever I mean thing you have considered for the isotropic soil, the same will be applicable here. So, elements will be approximate square. Now, the rate of seepage per unit length. So, now we are going to find out the rate of seepage. So, rate of seepage per unit length will be q, small q, equal to root over kx into kz into h n f n d, right, h n f by n d. So, that I mean if you know this n f, that is number of flow channels, and number of equipotential drop n d, and the head difference between upstream and downstream side, say h. So, then and if you know the permeability, coefficient of permeability in x and z direction, you can find out the rate of seepage per unit length in of the I mean barrier or the actual problem. Okay. So, note that when flow nets are drawn in transformed sections, the flow line and equipotential line are orthogonal. So, please make a note that when, because this transformation is made to take the advantage of this 90 degree intersection or the orthogonal intersection of flow line and equipotential line. So, when you are transforming in the transformed section, so when the flow nets are drawn in the transformed section, basically the flow lines and equipotential lines, they must be orthogonal, because by taking the advantage you are getting that thing from the mathematical expression. However, when they are redrawn in a true section, that means first you have got the true section or the true problem, then you are transforming that thing in some transformed section where the flow lines and equipotential lines, they are intersecting each other at 90 degree. Now, again you are redrawing the same thing from the transformed section to true section. Now, in the true section, when they are redrawn, these lines are not a right angle, not at right angles to each other. So, please remember this thing. So, in the actual or the true section, they are not really meeting at 90 degree, whereas in the transformed section they are meeting at 90 degree, because we have taken the advantage by transforming the coordinate system. Now, flow net can be used to determine the uplift pressure at the base of hydraulic structure. So, basically as you have seen, so flow net, the main purpose of the flow net is to calculate how much seepage or how much flow is happening through the permeable layer. So, that information you are getting if you construct the flow net, if you know the number of flow channels, if you know the number of equipotential drops, if you know the head and other things, you can find out the rate of seepage, right. Already you have seen that, whether you consider square element, whether you consider rectangular element, that is not the matter of fact, but the main thing is that you are getting the rate of seepage, but you can get other information from the flow net. So, what is that other information? That is that you can find out or you can determine the uplift pressure under the hydraulic structure, okay, by constructing the flow net. Now, we will see that how we can do that. So, suppose this is the problem actually, see you have say some kind of say small barrier, okay, so concrete kind of barrier which is holding the water on the upstream side. This is your upstream side, okay. The depth of the water at the upstream side is say 7 meter, and this wall or this concrete block is embedded at 2 meter in the ground, okay, and in the downstream side this is the water level. So, the difference between the water level at upstream and this is your downstream side. So, upstream and downstream side is say 7 meter, right. So, this is the head, that is a capital H. Now, the depth of permeable layer is say 10 meter, okay, and then followed by the impermeable layer here. Now, we are considering the soil is isotropic with respect to the flow, that means Kx equal to Kz equal to K. Now, we are constructing the flow net. We can construct the flow net, right, by following the philosophy for the constructing the flow net. Now, this is nothing but your one of the flow line, right, whereas these are all your equipotential lines. Okay. These are all equipotential lines. Now, basically if you can find out the pressure or the vertical pressure at point small a, small b, small c, small d, small e and small a, then basically you can find out, and you can, if you can plot the pressure distribution, then basically you will be getting the pressure at the base of the hydraulic structure. So, this is your concrete hydraulic structure. So, at the base of that structure you can find out, and then based on that uplift pressure basically you can determine the stability by considering the weight and all those things. So, that comes under the stability analysis of the geotechnical structure. So, now I mean how do we find out the uplift pressure at the base of this hydraulic structure? Let us see. So, basically if you see, so there are how many number of equipotential drops in the flow net. I mean this flow net whatever we have considered, though we have shown only one flow line, but how, I mean we are showing all the equipotential lines. Now, how many equipotential drops are there in this flow net? So, if you can count, this is 1, 2, 3, 4, 5, 6 and 7. So, you have got 7 equipotential drops, that means, so from this zone to this zone. So, this is given by, this is separated by this equipotential lines, right. So, similarly I can find out how many number of equipotential drops are there in the flow net. Now, so the difference in water level between upstream and downstream, that is given, that is I told you that will be 7 meter. So, these two informations we are getting from this flow net construction, and the head loss for each, therefore, I mean as you follow whatever we have discussed in the previous lecture. So, the head loss for each equipotential drop will be how much? H by 7, that is nothing but 1, right. So, H is 7, that is the total head loss. Now, for each equipotential drop, okay, what will be the head loss? That will be 7 by 7, that is 1, right, simply. Now, the uplift pressure at A, that is the left corner like this. So, left corner at the base. Okay. So, that is nothing but pressure head at A multiplied by the unit weight of water, that is gamma W. Now, what is the pressure head at A? So, 7 plus 2 is the total depth, right. 7 plus 2 is the total depth of water. Now, when you are reaching at A, so basically you are exhausting one equipotential drop. Do you agree with that or not? So, please try to understand this thing fundamentally. So, 7 plus 2, 7, this 7 plus 2, that is the embedment. So, this is the point A, that elevation of point A or the depth of point A from the top water surface at the upstream side is nothing but 7 plus 2, that is 9. Now, when you are coming to point A, basically you are exhausting the first equipotential drop, this one you are exhausting. So, 7 plus 2 minus 1, this much of loss you are accumulating, that is 1 is the loss. So, 7 plus 2, that is 9, that is the total head, minus the loss, that is 1, is equal to 8 into gamma W. So, that is the uplift pressure at A. Similarly, you can calculate for other points, say at B. So, if you see this is my point B. Now, at B what will be the uplift pressure? So, what is the head at B? Head is, I mean the depth of B point is 7 plus 2, 9 is the same, because A, B, C, D, all those things are lying along the base of the hydraulic structure. So, their elevation or their depth is same, right. So, 9 is the total depth, minus how much loss you are accumulating by going from the upstream side to point B. So, there are two equipotential drops basically, first one and the second one. So, two equipotential drops you are exhausting. So, the loss will be 2 into 1. So, 9 that is coming from the depth and 2 that is the number of equipotential drops, okay, to reach point B, and 1 is the loss for each equipotential drop. So, you are getting 7 W. So, that is your uplift pressure at the point B along the base of the hydraulic structure. Similarly, at F, that is the last point, that is the rightmost corner point at the base. So, what will be the uplift pressure at that point? What is the depth? Depth is same, that is 9, minus how many equipotential drops you are exhausting. So, if you count 1, 2, 3, 4, 5 and 6. So, 6 equipotential drops you are exhausting, each equipotential drop will be having say loss of 1. So, you are getting 3 gamma W. I hope that you have understood the concept, right. So, therefore, you can draw the pressure distribution at the base, that is uplift pressure distribution at the base. So, that means at point A you are getting 8 gamma W kilonewton per meter square, at point B you are getting 7 gamma W kilonewton per meter square, at point C you are getting 6 gamma W, at point D you are getting 5 gamma W, at point E you are getting 4 gamma W, and at the last point that is F you are getting 3 gamma W. Okay. So, this is the uplift pressure distribution. Now, if you what is the use of this? Now, if you want to find out the stability, that means uplift moment or whatever those things you can calculate. So, basically from this pressure distribution curve, what is the total force acting at the base of the foundation towards the vertically upward direction, that you can find out, and based on that you can find out the stability with respect to the uplift, right. So, this is very very useful to calculate or to find out the stability of the structure. So, and that you have got just by constructing the flow net. So, you have got the information about the advantage of the flow net construction. Now, coming to the seepage through earthen dam on an impervious base. So, now this thing also we can find out, say now if you have one earthen dam. So, that you can see from this figure. Okay. So, the earthen dam is there. Now, this earthen dam is resting on the impervious base, that means the flow, if the flow is actually happening, then the flow is happening through the body of the earthen dam, right. So, earthen dam is constructed to store the water. So, this is your upstream side, okay, where you are storing the water and the water level is say H, okay, and this is your downstream side. Okay. Now, basically if you see the flow through the earthen dam, what will happen? So, this is the entry point, okay, point A, small a is the entry point of the water, right, and it will go all the way to through B and C, and then finally, it will flow along the surface of the downstream side, okay, downstream slope. I hope you have understood. So, basically the topmost flow line is nothing but A, B, C as well as D, right. So, this is the topmost flow line along which the flow is happening. So, below that line